Hello and welcome to yet another video of Cornerstones of Math. In this video, I will solve the following problem from South Korean College Scholastic Ability Test, which is the test that high school seniors take in order to apply for the college. The most recent test for students who will go to college in year 2026 was held only a few days ago, and this problem right here is what I consider the most difficult, or should I say the most confusing problem. So let's take a look at it. For a cubic function f of x with positive leading coefficient and a real number t, function g of x is defined as minus f of x when x is less than t and f of x when x is greater than or equal to t. This function g of x is continuous on the entire set of real numbers and satisfies following conditions. Condition A: the limit of g of x divided by x times x minus 2 when x approaches a from the right side exists for all real numbers a. Condition B: the set of natural numbers m that make the limit of g of x divided by x times x minus 2 as x approaches m from the right side negative is the set with two elements, g of negative 1 and negative 7 over 2 times g of 1. Find the value of g of negative 5. And of course, these two elements from the set in condition B are different. So this is the problem about limits. I have already solved a similar limit problem from last year's CSAT, which was also problem number 21. I will provide a link in the description. However, this year's limit problem was clearly more difficult, so if you have trouble understanding the problem, please pause the video and carefully read the problem again until you understand it. For those who understood the problem, let us start investigating the conditions given in the problem. And let us actually start from this condition: that g of x is continuous on the set of real numbers, hence it is also continuous at x equals t, even if g of x is defined differently on the left and right side of this t. This means that the following two one-sided limits, one approaching t from the left and the other approaching t from the right, must be equal. As for the left-hand side, x is approaching t from the left, so we must use the expression minus f of x, and on the right-hand side, where x approaches t from the right, we use the expression f of x. In this problem, f of x is given as a cubic function with positive leading coefficient, which is a continuous function. Therefore, we can simply write minus f of t and f of t for the left-hand side and right-hand side respectively. This gives the result f of t equals 0. Therefore, g of t is also 0. Next, we move on to the first condition given in a box regarding the one-sided limit of gx divided by x minus 2. One thing to notice about this function is this. The denominator becomes 0 when x is equal to 0 or 2, and the numerator becomes 0 when x equals t, which I have just shown. Nevertheless, it is stated that the value of this limit exists everywhere. So how is that possible? Well, now is a good time to introduce these two useful lemmas regarding the limits in rational form, which I have also used in the last year's problem. The first lemma is that if this limit exists and the denominator goes to 0, then the numerator must also approach 0. And the second lemma is that if this limit exists and have non-zero limit value, and the numerator approaches 0, then the denominator must also approach 0. I'm not going to explain the proof in detail here because it's kind of obvious. If you assume that the conclusions are not true, then the existence of this limit just doesn't make sense. Now let us apply the first lemma to our case, where the denominator becomes 0 at x equals 0 or 2. This means that the numerator must also approach 0 when x approaches 0 from the right and 2 from the right. This means that either minus f of 0 or f of 0 must be 0, and similarly either minus f of 2 or f of 2 must be 0. Whichever case it may be, we can obtain f of 0 equals 0 and f of 2 equals 0. By the way, as for lemma 2, It is applicable when we know for sure that the value of the limit is non-zero. But that information is not given in the problem, so I'm not going to use lemma 2. For now, I'll explain it in more detail when it becomes relevant. Before we move on to the next condition, let us think about what can be inferred about function f of x from what we obtained so far. F of x is a cubic function with positive leading coefficient, satisfying f of 0 equals 0 and f of 2 equals 0. This means that the equation f of x equals 0 has 3 real roots. And by 3 real roots, I mean including the double roots cases, where 2 out of those 3 real roots are either 0 or 2. We still don't know in which of these cases does our f of x belong, so all we can do for now is to express f of x as positive leading coefficient p times x minus 2 times x minus k, which is the third real root. A bit of caution here. Some of you may remember that the value of f of t is also 0, where this t splits g of x into 2 cases. And some of you may want to use this as well. So, does this mean that we can express f of x as p times x minus 2 times x minus t? Well, not really.
Nope.
The problem arises when t is either 0 or 2. In those cases, the factor x minus t might be the already existing factor x or x minus 2. That is, there is no additional factor x minus t like this expression suggests. Therefore, this is still the furthest we can narrow down to. Now let's move on to condition B. The same one-sided limit that we discussed so far has negative values when m is the natural number in the set g of negative 1, negative 7 over 2 times g of 1. For now, just for the sake of simpler notation, let's call these two natural numbers n1 and n2, and we'll consider their relation with function g later. Using the previously obtained expression for f of x, g of x can be expressed like this. And if we divide this by x times x minus 2, the function becomes minus p times x minus k when x is less than t, and p times x minus k when x is greater than or equal to t, which is a linear function. Therefore, the seemingly complicated limit given in the problem is simply the limit of a linear function, which is quite easy to handle graphically. So let us examine the graphs of these two linear functions. The value of functions becomes 0 at x equals k, the third root of the cubic equation f of x equals 0. The graph is split into two parts by x equals t, whose exact values are still unknown. So we have to divide the cases by the position of x equals t, hence its relation with k. We can think of three cases. T is equal to k, t is greater than k, and t is less than k. For each of these cases, the graph of g of x divided by x minus 2 looks as follows. And with these graphs, now we are ready to tackle condition B. Let's start with the first case, when t equals k, where we have this symmetric graph. One noticeable feature of this graph is that the value of the function is non-negative on the entire domain. This means that the limit given in condition B cannot have negative values. Therefore, this is an invalid case. Let's move on to case 2, where t is greater than k. This time the graph has a negative value region. Let us investigate further. Let us consider the limit given in the condition when x is approaching t from the right. From the graph, you can notice that this limit has a non-zero value because it is the limit in this direction. However, we have already obtained that the limit of the numerator g of x, which is equal to g of t, must be 0. This is the part where previously explained lemma 2 comes in handy, which states that if this limit has a non-zero value and the numerator goes to 0, then the denominator must also go to 0. Applying this lemma to our case, the limit of the denominator must also approach 0 when x is approaching t from the right, which gives t is equal to either 0 or 2. According to condition B, the limit has negative values when x approaches n1 or n2. Therefore, natural numbers n1 and n2 must exist here. That is, two natural numbers n1 and n2 are in between k and t. However, this is impossible when t is equal to 0 or 2. Therefore, this case is also an invalid case. Which leads to the third case where t is less than k. Let us fast forward a similar process. Investigating the given limit when x is approaching t from the right, that is, this direction, the entire limit is non-zero, but the numerator goes to 0, so we can apply lemma 2 again, which means that the denominator goes to 0, hence t is equal to 0 or 2. There are two natural numbers n1 and n2 that give negative limit values, which exist here. So this time, they are both greater than or equal to t and less than k. Notice that t is also a possible value because we are dealing with the limit approaching from the right. This is possible for both t equals 0 and t equals 2. Therefore, we have to divide into two cases again. When t is equal to 0, then two natural numbers n1 and n2 must be 1 and 2. We have to start from 1 instead of 0 because n1 and n2 are natural numbers. And this k must be greater than n1 and n2, so k is greater than 2, but it must be less than or equal to 3 because there has to be only two natural numbers n1 and n2. And when t equals 2, then n1 and n2 are now 2 and 3, and k must be greater than 3 and less than or equal to 4. First case when t equals 0. Let's write the condition for k first, which is that it must be greater than 2 and less than or equal to 3. And then we have n1 and n2 must be 1 and 2. And now let us relate these numbers to the values of function g. We have already obtained the expression for g of x, and now with t equals 0, the function is split into two regions, x is less than 0 and x is greater than or equal to 0. Now let us carefully calculate g of negative 1 and negative 7 over 2 times g of 1 using this expression. Negative 1 is less than 0, hence we must use the first expression for g of negative 1, and 1 is greater than 0, hence we must use the second expression for g of 1. In the end, we obtain that g of negative 1 is 3p times k plus 1, and negative 7 over 2 times g of 1 is negative 7 over 2 p k minus 1. So these must be 1 and 2, but observe this. We have the range condition k is greater than 2 and less than or equal to 3, and we also have the range condition for p, which is that p must be positive. In this case, the second expression for negative 7 over 2 g of 1 is always negative, meaning that it cannot be the natural number. Therefore, we can easily determine that this is an invalid case. Second case, when t equals 2. In this case, k is greater than 3 and less than or equal to 4, and n1 and n2 must be 2 and 3, and let's do the similar process. We have g of x right here, which is now divided by t equals 2. Notice that both negative 1 and 1 are less than 2. Therefore, when calculating g of negative 1 and negative 7 over 2 times g of 1, now we must use the first expression for both values. This gives g of negative 1 is 3p times k plus 1, which is the same, but negative 7 over 2 times g of 1 is now 7 over 2 times p times k minus 1. And these must be 2 and 3. Unfortunately, we cannot decisively determine which one is the larger number, so we must consider both cases. The case where 3p times k plus 1 is 2 and 7 over 2p k minus 1 is 3, and the case where 3p times k plus 1 is 3 and 7 over 2p times k minus 1 is 2. Notice that the first case gives negative values for both p and k, making this an invalid case. The second case gives p and k values that satisfy our range conditions, which is that p must be positive and k belongs to this range. So we have finally found the valid case. With these obtained values, the remaining step is easy. Our cubic function f of x is 3 over 14 times x minus 2 times x minus 11 over 3. Hence gx is given like this, defined differently in x less than 2 and x greater than or equal to 2. The end goal is to find the value of g of negative 5. Since negative 5 is less than 2, we must use the first expression when doing so. So substituting negative 5 in the first expression, which gives the answer 65. This was indeed a tough problem to test students whether they have a solid foundation of limit knowledge as well as deep reasoning skills, and was definitely more difficult than last year's problem number 21, which you can check by clicking on the top left video shown here. Also, don't forget to hit the like button if you enjoyed this video, and I will see you in another video.